Okay, so what I'll do today then is I'll spend actually maybe what I should do is before getting onto the next thing, spend some time going over asking for questions. So anything from last time, again, except for this thing that I'm confused about that I just mentioned, or anything so far, because what I'm going to talk about today is it does fit together with the stuff that we've been doing so far, but it's somewhat independent of it. It involves some new ideas, and so if you're confused about something earlier on, nothing I say today should help. So maybe it's a good time now to ask for any questions about anything so far. No. Can't convince everybody. Everything so far has been completely clear. That's hard to believe. Okay, well, anyway, I'll also, again, give you a chance also to see me afterwards, ask questions. But then if there's no questions about the material through chapter 8, let me then start on what I'm going to do today, which is tell you about tensor products. Okay, and one thing I realized is that there's, so this is something which, well, anyway, let me just get started on this. Okay, so what's going on here is in some sense it's a very basic kind of fact about algebra. So if you're given two vector spaces, so let's say V V and W. Okay, and so what I'm telling you is kind of true in some, for very general algebra over general fields. But you should think of these are vector spaces either over the real numbers or over the complex numbers. You should think about it. Okay, then what you can do is you can form a new vector space. Well, the first thing to think about, which is VW, which we'll write this. You can think of it as kind of the sum of these things, and this is just and this is just the elements are pairs of V and W, or V W. Okay. And then the dimension of this is equal to the sum of the dimensions. Okay. So this is kind of completely stupid, and then but I mean we often use it, and so for instance we used it when we were talking about irreducible representations. A representation was irreducible if you couldn't write it. If you couldn't write it as put together in this way out of two smaller representations. Okay, and then the basis elements. Okay, so if E1, how do I do this, up to E, the dimension of V is a basis of V, and F1 up to F dimension of W is a basis of W. Then you just, if you want a basis for V plus W, you just put together these guys and these guys. So then E1, E in V is basis. Okay, so this is, anyway, this is all kind of completely kind of dumb. There's really kind of nothing particularly non-trivial going on in this whole construction. But there's another construction. So anyway, that's that. So this is easy to, and if you want to do and in terms, if you want to write things in terms of column vectors, you write elements as just think so something here that's in V and something here that's in W. So that's in W. So in other words, you just make a bigger column vector sticking the two. So this is really just a thing where you just stick two pieces together, and they don't interact with each other in any interesting way. Okay, so now the thing is there's a much more kind of non-trivial and more interesting vector space that you can make out of these vector spaces, and so this is going to be the tensor product. Okay, so you can form a new vector space. It's the tensor W. Okay, and how do I want to? Okay, now there are various ways of motivating this. So maybe one way of so try to decide. So the simplest definition is this is the vector space basis. This elements on EJ tensor FK, so this is one. In other words, you take one basis. This is one of the basis elements from V, and this is one of the basis elements from W, and you put these and you anyway, and then you just give this a name, and that there's going to be there are dim V times W. Okay. So anyway, so one way of saying this is, okay, well, this is what this is going to be is it's going to be I'm just going to anyway I'm just going to create do it this way. And now the problem with this definition, the reason, I mean, mathematicians don't normally kind of like this definition because this definition is really basis independent. The problem with this definition is that if you use this definition, then you have to worry that anything that you do with this construction, you have to show that it's basis independent. Because normally we don't kind of like doing things in linear algebra or these. Well, we want to do things in a basis independent way, but we've actually define this whole construction in terms of a specific basis. So that's the problem with this definition. But it is one that works. So there are I'm trying to think to tell you. So anyway, but the problem is that if you try and come up with a basis independent. So let me just kind of say this is that basis independent definitions are very abstract. So if you go and look at you pick up a typical kind of math textbook on abstract algebra, you can look for the definition of this thing, and you'll often find some very abstract thing that you do some very large construction and take some quotient by some relations, and then you get this guy. But it's a hard fit. These are kind of not very. This is very practical, easy to work with, but it's not necessarily basis independent. These abstract definitions are kind of very non-concrete and hard to work with, but they are basis independent. So what I'm going to do is try to tell you some properties. I'll tell you some properties of this construction, and I won't actually prove that these things work. You can work them out in terms of the definition, in terms of the basis, or you can work them out in terms of an abstract definition if you want to find one and play with that. But the crucial thing is more kind of what you can, what you can do with this space. So let me to start this. Okay, let me. So I'm going to try to decide what to do. I think let me just kind of tell you a bunch of things about how this works. So maybe before I do that, maybe give another motivation. So you can think of, so since v vector is equal to v1, e1, en, en. So if you write out a vector with respect to a basis, then you can think of this as as a function on the basis element. Okay, on the set of. So you can think of so you can think of what's happening here is that that an arbitrary vector space you can think of as a vector space of functions on a set, but it's this finite it's a finite set of basis elements. But what you want to do is okay, but then what you can think of a V. So you can think of V as the functions on this finite set of basis elements. But now the question is then V cross tensor W is going to be the functions on the product space which is a basis elements of V cross. So what's happening? So if you think of anyway, very often it's a good idea to think of your vector space as a vector space of functions on something. Well, for any vector space, you can think of as a functions on this space. This is just a space with dim v points, and this is a space with dim w points. So the tensor product construction is really the construction you get when if you're passing from if you're alwaase thinking of your vector space as a vector space of functions on something. If you take the set-wise product of these two sets, then the space of functions you get is this guy. And so one way that this is going to anyway, so whenever your vector space is a set of functions on some space, then if you've got two of these, if you want to take the look at the set of functions on the product space, that's going to be that's the tensor product. So it has that's one way in which this kind of often appears. Okay. Trying to think. So there's just so then in terms of working with this. Okay. So what you want to do is, given any B and D, W and W, you can write this thing out with respect to the basis, this thing out with respect to the basis, and then there's a you can define the tensor W of the tensor product. Okay. So in other words, so I mean, if you just write this thing out and expand it out, you'll get an expansion in the basis elements, the EJs and the FKs are over here. If you just expand the thing out, and that will be, so that will be something. Anyway, that will be something in here. So one thing that happens. So the other reason why this is interesting is, I guess, that it gives you a product on vectors. Normally, you don't actually have a vector space. You can just add things. You can't multiply them. Well, here, if you've got, you can multiply two things, but if you multiply two things, you don't end up in the same space. You end up in this product space. Okay, and then this behavior. Anyway, and then this behavior. So this product is bilinear. On both sides. In other words, if you take this guy, if you take some linear combination here, you get some anyway. You get a linear combination of things, and same thing on both sides. So this kind of has nice linearity properties, both in terms of it's linear in V and linear in W. What else does it have? And it turns out that it and you can show it's not initially obvious, but it's not hard to see that really it doesn't matter which order you pick here. That V tensor W is there's nice morphism between these guys. So these are anyway. You can identify these spaces. So it doesn't. So in practice, it doesn't matter which one you have first. The ordering doesn't matter. This isn't a non-commutative kind of problem, and it's also associative. Also, you tensor. There's isomorphism with. Anyway, so it has a nice kind of product properties in this very kind of somewhat abstract sense. Okay. Now what we're so we're interested in maybe actually say first a couple other things first, and then there are some other places that this occurs. So it's often you have a fact that what is it? Very often you want to look at linear at what I'll call VW. So this is linear maps from this vector space to this vector space. Well, it turns out that this can also be thought of as L as the dual space tensor with W. How do I want to do this? So that if L, so if you have L or W, this is the anyway. This corresponds to the linear map that takes V. So it takes you want a linear map that takes something in V to something in W. Well, you take what L V goes to L of V times W. Anyway, and then it's very the other way the tensor product construction is really useful is that it allows you to kind of go when you're talking about kind of spaces of linear maps from a space to another. It's a bit instead of thinking of it as the space of linear maps, you can think of it as a tensor product. This kind of breaks this up into a way that's often easier to handle. And let's see, what else do I want to say? There's another motivation. And this, so we're going to be talking about so some of the vector spaces that we're going to be looking at are often going to be like spaces of wave functions. They're going to be functions on some space, and this motivation that the tensor product is the thing which gives you functions on the product space. Is that this is let's pick some space of functions. Let's say square integral functions, so L2 functions. So if you take L2 functions, so just functions on the real number line, that the tensor product of these is going to be what you get is what you get if you want to Rn. So say n times. Okay. So sometimes we'll find it's useful that if we want to think about functions on the set, which is kind of the on a set like this, it's going to be given by this way. Okay. Let me see if I want to say that maybe then there's one more thing which I'm often going to use. As I talked about complexification. Yeah, I mean, I kind of often said this in words, but you have to actually see what does this actually mean, and what this actually what I really mean by complexification. So give for if of a real vector space. Space V is V tensor tensor C. But the point is that this is with we're thinking of C as a real 2D. So here, here as real vector spaces, this would have basis 1 and I, and this guy would have a basis whatever E1 up to E in V. And then if you want to know what the complexification, whenever I've been talking about the complexifications of a real vector space, what I really mean was the tensor product, the tensor product which you get by taking, you know, pairs of one of these and one of these, and then that gives you a real vector space, but it gives you a real vector space of twice the dimension. But it's one on, but the fact that it has a C here means you also have a way of multiplying by complex numbers. So you've turned a real vector space into something twice as big, which is a complex vector space. And this kind of abstract way of thinking about it is the thing which kind of makes sense when you may be given this in a confusing form. You may be given this as a something defined in terms of complex numbers, but its elements are only, but it's a real vector space that you're only allowing real linear combinations of those of those things built out of complex numbers. So this is the kind of abstract nonsense you need, and you have to be careful when you're talking about tensor products. You know, what's the underlying field that you're using? So here, this is all over real. So sometimes you say that there really should be you should put an R here, which means that this is the, I'm thinking of this as a real vector space and this is a real vector space and taking the tensor product. If I thought of this as a complex vector space, and this is a complex vector space, and took the tensor product, then this would only have one basis element, and I wouldn't actually get anything new. So anyway, these are just some of the ways in which this construction is going to show up over here as we go on. Yeah.
So, Professor, in that complexification, the reason that you're not taking C as a one-dimensional complex space is so that you can use the same field for both, and so that you get these two basis elements as opposed to one.
Yeah, because otherwise, if I took instead, let's say, yeah, but let's say that you give me, I have V as a complex vector space, and C as a complex vector space, and I take their tensor product as complex vector spaces, then this is going to have some. This is going to have some. So I got to remember. So this is going to have some basis. It's going to have some complex basis. It's going to have a basis of you know, all the things you need to do to get that by multiplying by complex numbers. So this is going to be, you know, some basis again, but it's a complex basis. E given V. And but this guy as a complex vector space, he just has one basis element. He's just one dimensional, right? So if I tell you, you know, take let's form a new vector space whose basis elements are these guys paired with the things in here. Well, there's nothing new. As you know, you've got nothing new. You've just got, because the, you know, every, you know, the, you know, EJ or EJ tensor one. I mean, it's the same thing. You haven't constructed anything new. Yeah. So this is actually V itself. This is true. But this guy is not equal to V. He's a real, anyway, yeah. So he as a tensor product, he's a real vector space of twice the dimension. But because he's built out of these C's, there's actually, he also has a complex structure now. You also know how to multiply complex numbers by him, because you use it using, anyway, using the kind of the bilinearity on the C side and the C comp that you have C. So it's a bit confusing, but this is the, anyway, this is the right piece of kind of abstract nonsense to say exactly what I mean by a complexification. Okay. So these are, yeah. Yeah, what?
Oh, a follow-up is that, so can we interpret B as a complex vector space and then tensor product with C as a real vector space? Like, it's, I guess, like,
well, this is a, yeah, well, so the complexity, so the idea of a complexification is you start with a real vector space, I already mentioned, and then you want to well, and I'm not sure what to say. I mean, this construction clearly gives you something gives you a new real vector space whose basis elements are these guys and then one of these guys. So there's twice as many basis elements, right? So as a real vector space, this guy is twice, the real dimension of this guy is twice the real dimension of the tensor R of C is 2 times the real dimension of V, right? So you increase the dimension, but the thing that then you get that's extra, you haven't just kind of, I mean, the fact that everything, I mean, you can now use the fact that on one that things are linear in C, and so you know how to multiply. Anyway, you now know how to multiply things in here by complex numbers because you just do the multiplication on the C here. Okay, I don't know. So plus the tensor R C has a complex vector space. Okay. I mean, this is all maybe all kind of confusing, but whenever I write down, whenever I say I complexify a real vector space, I mean I'm taking something twice the dimension with the basis elements that are pairs of the original basis elements and 1 and I, and then so you've got something twice as big, and the fact that you've got basis elements 1 and I means you can this gives you a rule for how to multiply by complex scalars. Because your problem was that this guy, if you just took V here, there's no obvious rule. There's no necessary rule of how to multiply him by complex scalars. If you take these pairs like this, then there's a simple rule for how to multiply these pairs by complex scalars. You just multiply these guys by the complex scalar. Anyway, I hope that helped. But this is a bit too. This is a bit more abstract than really that useful. Let's see. So, what I want to maybe. Okay. So this is all a bit kind of too abstract and too much abstract nonsense. But maybe the kind of the piece of abstraction I really care about is actually this. That if you actually have a I want to say that. Yeah. So if you if A is a linear operator on V, and V is a linear operator here on W, then there's you can form a linear operator. You can kind of tensor that. You also get a tensor product of the operators. Is a linear. It takes on the tensor W. It takes V tensor W goes to AV. Okay. Yeah. So you get so because of the bilinearity of this construction, you also it also takes. Anyway, you also get a tensor product of the linear operators on there, and so you can look at these tensor product linear operators. Okay, so now maybe before I'm trying to think if I should get onto the quantum mechanics. There's something else that I thought before I get onto the application of quantum mechanics. Actually, let me go through the quantum mechanics stuff quickly, and then I realized it might be a good idea explain what the relationship is between this story and the standard and the story that you'll often hear if you've taken other physics courses. You've often hear about tensor fields, and so I thought maybe I wanted to tell you what the relationship is between this story and tensor fields. But maybe that's a bit complicated. But let me kind of first do the applications to quantum mechanics or representation theory that I wanted to do. So the first one was really to use this. And so the idea is, so the application of quantum mechanics, QM, is, and it really, this construction is the one thing that actually gives you a sensible way of kind of putting two systems together. So if you have, given a quantum system one with states H1 operators. Let me just call anyway. So you've got, let me call the space of linear operators that you have acting on this thing. So this is kind of what abstractly I've been claiming is you should think of it as good some quantum system is going to be. It's a complex vector space with some set of linear operators on it, which are, and the self-adjoint ones here are going to, are going to be the ones that are going to correspond to observables. And then two with states H2 and operators, some set of operators O2. You can form. If you're asked the question, what now? Let's say that I want to. I've got these two completely independent quantum systems that have nothing to do with each other. But I want to. If I believe that there's some way of thinking of these two things as being two components of some more complicated thing which I'm trying to study, like this may be describing one kind of particle. This may be describing another kind of particle. What if I bring these particles together and I want to ask what they're, how are they going to, and I want to kind of set up some quantum system that allows me to talk about the, how these things are going to interact with each other. I need some kind of setup where I can put these systems together, and then so you describe a composite system by states H1 tensor H2 and operators A tensor B, or A is from the set that operates on here, and B is from the set that operates on here. So this is kind of a, this particular piece of algebra that I've been talking about turns out to be that if you try and think about, what is it, what's the possible consistent way of talking about something that's got these two independent things in them, but I want to be able to talk about non-trivial interactions between these things. Well, it's the tensor product is the thing that does it. So this is kind of the physical, in some sense, the physical motivation. I'm not sure. Anyway, how strong you want to feel that is, but it turns out this is actually, in practice, when you've got problems, when you've got two independent things that are easy to understand, and you imagine bringing them together and doing something to each other. This turns out to be exactly the right formalism for discussing that. So that's the physical motivation. The
Professor?
Yeah.
So built into the tensor product structure, is there much interaction between the two systems we've combined, or do you add new structures that give that interaction?
Okay, well then it's going to be so. Well, so the things that are going to be so the inside here you're going to have. So you have operators. Okay, maybe this is a good time to say something like this. So you have. Okay, well, first something about operators. So inside the operators here, I mean, one operator you always have is the identity operator. So operators. So you have. Operators A tensor the identity and one tensor B. Okay, so operators of this form are going to be what you would call kind of non-interacting. That they've got the operators of this form just describe the story that you were doing about you had about H1, and there's really nothing interesting going on with H2, and here are the opposite. But the point is that so interactions are described. Let me just say so then interactions are going to be described by something more general, where you don't just have the identity here, or not just have the identity here. So within this huge tensor product setup, you have each of the things independent systems, but you've also got the ability to think about operators which are non-trivial on both sides. And those are going to be the corresponding interactions. So that's and I realize so that's one thing. Okay. And then actually maybe there's just one other thing to say about at this point, which is it's going to reappear here. And then the other way that this occurs is that so you can describe if H describes a single particle, well then H tensor H describes so this is n times anyway so n times this describes a system of n particles. But there's something then there's kind of a something else that very interesting that happens in quantum mechanics, which is kind of unexpected, that because there's a fundamental indistinguishability of particles in quantum mechanics, you end up that you don't actually want to. It turns out you have to take symmetric or antisymmetric part. So it turns out if you're actually describing a system of so this describes a system of distinguishable particles. If you've got identical indistinguishable particles, which is what the elementary particles of the real world seem to be, then you have to take you have to describe this by the subspace of this tensor product of things that are invariant under all permutations of the vectors of the tensor product. But let me go. Let me not kind of say more about this. This will come up later, but it's another way in which this occurs. Okay, and then maybe another thing to say about the physics is that what happens. So you should note. Includes V, so W includes V, so V, it includes things like this that are products of something in V and something in W, but also enter W1 plus so these are called decomposable. Well, these are called indecomposable. Yeah. Oh, let me say indecomposable. So the slightly confusing thing about this is this isn't just a product in the sense that elements of this guy are not just products of two vectors. If you take products of something in here, tensor product of something in here or something in here, you can get something in here. But remember that this is a vector space. You can do two such things and add them, or you can do as many as you want. And in general, if you do this construction, you can't write a typical thing in here. You can't write in this way. And this is what's going to correspond to the things like this are going to be what are called entangled. And these are the things which you get into trouble about kind of how to interpret, how to give some kind of classical interpretation of what these things mean. I mean, this thing here, if you take V as some eigenvector of some operator, so the observable, it has a certain, if V has kind of a well-defined value for some classical observable, W has a well-defined value for some classical observable, then you put the system together, and and states like this kind of make perfect sense. You've just got, there's a well-defined notion of observable of what observable to associate to these states. The problem is here, if you do it here, if you add together things like this, these things even if V1, W1 were eigenvectors for some operators in these two sides, in these two different kinds of states, and V2, W2 were also eigenvectors. If you put this together, you're going to get something which is no longer an eigenvector for those operators. So it's a so there's really, you don't really know what if you have the fact that you can write down states of this kind, then means that you can you can no longer assign kind of physical properties to these composite things in a way that you thought you could. So I won't get into this. This is kind of the beginning of all sorts of interesting discussions of what you can do, of kind of some of the paradoxes of quantum mechanics. Okay. Okay, so I better start. So let me stop talking about the general story about this. This is the kind of standard physical story, just with saying some very abstract things about it. But now let's go back to math and to this claim that the way operators are going to come about is from some Lie algebra representation. So what happens here is that if I want to write this down, sorry. Okay, so if we really click that, if pi v v and pi w are rep of g. Okay, so in other words, I got two vector spaces on which G is represented, and these homomorphisms are given by two different things called pi v and pi w. So these are just whatever representations we know about on two vector spaces. Imagine just taking two of them, taking two different ones, or the same one, and then you get pi. And it's just given by the IV tensor W of G is just remember that we can take tensor products of linear operators and get an operator in the space. So you just take pi v of G and the tensor product as operators for this guy. So there's kind of this fairly trivial construction, abstract construction that tells you that if you know that you can take representations on a space, and you know, I mean, the sum, we could have done this with sums. There was this kind of trivial way of glomming things together to get a representation on the sum. This is a new thing. It gives you a representation on the product, and it's given by it's given by this. You use the fact that we know how to define the tensor product of two operators. Okay, and then I won't let me not take the time to do this. But then there's something funny happens that if you at the Lie algebra level. So another what you find is that if you try and take write G as e to the tx for something in the Lie algebra, and then now let's take the derivative at so in other words, take G is equal to e to the tx, take derivative ddt at t is equal to 0. So at the Lie algebra level, you get operators that are you get a Lie algebra representation, which on X. So this is something which this acts on the tensor product, and the way it acts, if you look at what it does on vectors of this form, and you can tell what an operator is going to do on the whole tensor product once you know what it does on these decomposable vectors, because anything in here is a sum of things in here of sum of things of this form. That there's a calculation in the section 9.4, but you can check it out. But basically, if you work at what happens, you find that you have to use the product rule when you take a derivative, and the product rule tells you, the Leibniz rule tells you that you get pi prime v of x applied to v, and then you leave w alone, and then you get v tensor pi prime w of x applied to w. Okay, so in other words, okay. So this acts. So this guy is pi prime v of x tensor, the idea, so he's got a piece which does nothing on the W side and does what it was doing before, and does what it should do on V, and then it's got a piece that's got the identity on the V side and acts this way. Okay. So you have to watch out. So the definition at the group level is just this normal product, but since at the Lie algebra level you're taking a derivative, the derivative of a product by a Leibniz rule means you're going to get a sum of two things like this. And there's a little bit more of an argument in the book. Okay. Okay. So now let's. So now let's go back to what we were talking about before, which was SU2 representations, and you can ask the question, what is a so given VW to SU2, which representation is V tensor W? And so this is kind of now a significant problem, a general problem in representation theory. That if you know about all the irreducible you know about any representation, you can break it up into irreducibles. And if you take a direct sum of two representations, then you're just putting together the list of irreducibles in the obvious way. But this in general is a hard problem. It's a hard problem that if you take, you know that there's a representation on the tensor product, and you know that all representations are decomposable can be decomposed into irreducibles. But if you start, so you need to know. And let's just say that so I'm not going to write the pi's, but let me just say that Vn. Is this the notation I use here? Yeah. So Vn1 is the spin 1/2. So and Vn2 is the spin 2/2. So in general, if I want to figure out what happens if I take the tensor product of two representations, I break both sides of the tensor product up into irreducibles, and then I'm multiplying irreducibles, and I have to figure out what happens with the irreducible. So I have to figure out what is Vn1 tensor Vn2. Okay. So the question is, what is this? And all I know from abstract nonsense is that any representation can be broken up into irreducibles. So this guy is a direct sum of SU2 representations with different values of the spin, but we don't know which ones. And it turns out, let me just write out the result, and the result is you get V. You get the sum of the two. That the guy who's spin n1 plus n2 over 2. I mean, if you take the sum of the spins, you get him, and then you get the same thing with where you take the sum and then reduce the spin by 1 or reduce the n by 2. Okay, so you got and then you keep going, and the place you stop, the lowest dimensional, the lowest one is going to be given by the v with just the absolute value of the difference between n1 minus n2. Okay. So this tells you this, and this is something called the this is called the Clebsch-Gordon decomposition. And if you try and prove this kind of by direct attack, by using the definition of a tensor product and looking at the tensor product representation, and when you can kind of there is a way to do this where basically you look at the tensor product representation here, and you find inside the tensor product representation you find this representation, and then you say, okay, now what about now what about the complement? What about the the orthogonal subspace to this guy? And then you find this guy, and then what about the orthogonal subspace to these two? And you find another guy, and then you find stuff here. So it's a complicated argument to try to do that. You can do it. There's something which looks like I've run out of time to tell you about, but there's a simplest argument is look at the characters of X, and these are functions. You take the trace v of g on pi, so trace pi. So to trace on v of pi of g. Okay. So these pi of g's are matrices, and so what you can do whenever you have a matrix, one for each g, is you can take the trace of the matrix, and then the trace matrix is a number, and then what you find is the maybe I should say this. I should say just say it this way. Just the trace is that you find that the trace, and this is something called the character of the representation. What chi v g, and then what you show that you show that the chi v tensor w, that the characters are multiplicative. So what you do is one way to understand how this Clebsch-Gordon thing works is to look at these functions which characterize the representations, these so-called characters, and then the tensor product representation in terms of characters has this very simple behavior. Then what you can do is then ask look at the question of what's the character of a you have to compute the character for a spin n/2 representation. That's not so hard. You know what the thing looks like in terms of weight, so you can just take the trace. And then let me then kind of tell you work out a couple quick examples which are important. And so what you want to know is this. So example v1. So these are the spin half representations. So if you take a spin half representation, tensor product of the spin half representation, you're going to get a v2 plus v0. Okay, so this is 1 plus 1 is 2. You drop by 2, you're down to 0. That's the difference between these things. And so what this says is that spin half times spin half one plus spin 0. Okay. So what this said, this is kind of the beginning of what happens if you try and study the question of, let's say that I got, instead of just these simple qubits we were talking about, what if I put two of them together? So if I put two of them together and start asking about these SU2 operators, what are they going to do on them? Well, they're going to act on you're going to get the they're going to act by the spin 1 representation. So you're going to get the operators for a spin 1 representation, and you're going to get the operators for a spin 0, just the invariant, And what and maybe let's see. So one way to say it is that, well, okay. So maybe to be a little bit more concrete. So basis elements of V1, are kind of 1, 0 tensor 1, 0. It's this thing 1, 0 tensor 0, 1, and then 0, 1 tensor 1, 0, and 0, 1 tensor 1, 0. Okay. Okay. So what this so what this space is, if you want to try and think about it concretely, what is this tensor product space of the product of two spin representations? Well, it's a 4-dimensional. This is a C2. This is a C2. You're taking all complex linear combinations of these guys. It's a C4, and so this is a basis of C4. And what this tells you is that if you act, is you have an action of SU2 on the C4, which splits into a C3 plus a C. Okay. So what this is saying, and this is I think I worked this out in the book, or it's an interesting exercise to look at, is that among these 4 basis elements, there's some linear combination which is invariant under SU2, and you can find that, and then there's then the complement of the space is 3 complex dimensional, and that behaves like under SU2 like a spin 1 representation. Okay, so I think I better just stop here. There's more in there, and there's also something. There's something again at the end of this chapter. There's a bunch of stuff about the relationship between tensor products and bilinear forms, but which I threw in there because I'm going to need it later. But I think we'll leave that alone until we actually need it. I guess that the one thing I would like to have done today that I didn't get a chance to do is to tell you a bit about what's often confuses people if you've had a good education among the physicists is that at some point they've told you about tensor fields, and the question is what does these tensors have to do with the tensor fields, and maybe just kind of one word about that if you've seen that. It's just the tensor fields. So from this point of view, so tensor fields are functions on and you can do this on Rn, or you can do it on a curved space on let's say a manifold n, and I take value in the vector space. So if you're that at x, oh, M in the tangent space to M. Okay, so remember that. So manifolds are things. One thing that they have is a nice linear approximation at each point called the tangent space. Well, something. So there's one thing that you have whenever you have a manifold is you have things called tangent vectors, and to the manifold, and those are just functions which at each point give you a vector in the tangent space. But the point is, and then you've also got things which but the point is that you can also take the tensor product of these many times as you want. Okay, and so you can get things that you can look at things that take values not just in the vector fields, but in the tensor product of a bunch of the vector spaces. And then to make it more interesting, you can also throw in things that take values in the dual space to the tangent space. And again, you can have a bunch of these. Okay, so if you know a lot about tensor fields and have heard about them, you can try and understand the relation to what I've been telling you about today. That it's what these tensor fields really are is there are things that there are functions which take values in a big vector space, and that big vector space is this tensor product. Okay, and so physicists, often they often don't have this language, so they have to go through a lot of kind of contortions to try to figure out how to define a tensor. But once you have this language, it gives you a nice definition of what a tensor field actually is. But I think I better stop there. But if people have heard more about tensor fields, about geometry, and want to talk about that sometime, I can talk about that. Okay, so sorry, but better stop now. Are there any questions? Any questions for today? And again, or you can come back in a little while, and I'll try to talk to people at more length. But nothing. Okay. Yeah.
One quick question. So you talked about indecomposable vectors. Can you do this? Are there operators the same form? Can you compose matrix or linear operators through addition and create linear operators that can't be decomposed?
I guess, yeah. I mean, I guess I haven't thought. That should be. Yeah, that should be true. Yeah, this is the same thing. The same thing should be true. That you have the same problem. That it's the tensor product construction. It isn't just adding together. It includes things that are these products, but it includes all linear combinations of products. So yeah, same thing is true of operators, I guess. Yeah.
Thank you.
Okay. Any other questions? Okay, let me stop for now, and anyway, sometime between now and I'll try to anyway. So plan on getting something that you need about 3 hours to work on sometime on Tuesday. And if you have any questions between now and then, if you're studying this and you want to talk about this, I'll be around and available most times between now and then. So just send me an email if you want to talk sometime about any of this. Okay. Okay. So bye for now, and I'll shut this down and connect back to the other thing in a minute. Okay. Bye. Bye.